Okay, so last session we discussed how to solve the circuits having a sinusoidal excitation. So last time we discussed one example. So we have this kind of a circuit having an inductor and a resistor and this particular source. So this is 4 ohm. So this is 1 Henry and this source is defined as Vg and Vg is actually equals to 6 cos 2t volt. So we have a voltage source which is a kind of alternating type, and this voltage source is defined as 6 cos 2t, and we have an inductor in the circuit and a resistor. So we are asked to obtain an expression for this current IT. So then we can basically apply Kirchhoff voltage law for this network. So the voltage across the inductor is basically L times the derivative of the current, and the drop across the resistor is basically resistance times the current. So which is equals to the voltage drop across the source equals to 6 cos 2t. So if you substitute these values, L equals 1 Henry and R equals 4 ohm, so then we'll basically ended up with this kind of a differential equation plus 4 times IT equals to 6 times cos 2t. So this is our first order differential equation. So then we came up with a kind of a trial solution for the forced response. Find the forced response. Find the forced response. So we can propose a forced response as A cos 2t plus B sin 2t. So then if this is the solution of this differential equation, so we can basically substitute this solution to the differential equation, which may definitely satisfy the differential equation. So once you substitute it there and evaluate the values, so we can basically get this. So we found that this is equals to 6 divided 5, if I remember correctly, it's like, it's something like that, cos 2t plus 3 divided by 5 sin 2t. So this is the forced response. So if you want to find the natural response, natural response. So we can get the characteristic equation. Characteristic equation. So the characteristic equation is basically S plus 4 equals 0. So then from this you can basically get S equals minus 4. So then basically the natural response is equals to a kind of a constant e to the power minus 4 times t. So this is the natural response and this is the forced response. So then the entire response would be the sum of these two, I natural plus I force. So then it's something like that. K times e to the power minus 4t plus 6 divided by 5 cos 2t plus 3 divided by 5 sine 2t. So then substituting initial conditions, we can find K. So if you know the initial condition of the inductor, we can basically find the unknown constant K by substituting initial conditions. So this is yes. So then we claim that. Using Euler transformation, we can convert this complex exponential into kind of a Cartesian form. So if you have a kind of a complex number having a magnitude of R, so this magnitude is R and the phasor is actually theta. So if you basically define this in the form of R and theta, so you can simply say that this is R and angle of theta. So this is the magnitude and this is the phasor. So then this kind of a complex number, complex exponential can be represented using a Cartesian form. So this is the real component of this and this is the imaginary component. Okay, so then by looking at this, we can claim that R cos theta is actually the real component of R e to the power j theta. Similarly, R sin theta is the imaginary component of R e to the power j theta. So based on this conclusion, we can do a kind of a substitution to evaluate the phase response of the previous scenario. So here we have Vg as 6 cos 2t. So what we can do here is based on this argument. So this is actually equals to the real component of 6 e to the power j 2t. So the 6 cos 2t is basically the real component of 6 e to the power j 2t. So then if you want to find the force response when we apply this source which equals 6 cos 2t, so we came with a trial solution A cos 2t plus b sin 2t. So if you have a sinusoidal excitation or a sinusoidal type of a source in the circuit, so definitely the right hand side of the differential equation would be kind of a sine function or cosine function. So then for that particular scenario, the force response would be, can be represented as a cos omega t plus b sin omega t in general. So this is the a very general format of replacing any cosine or sinusoidal term appear as a force term in the differential equation. So then depending on the a and b value, we can think of whether the response is aligning with the cosine or sine or kind of a combination. So at the same time, we discuss that we can further simplify the sine cosine combination into a form. So this form. So you can have a tilde cos 2t plus or minus theta. So then we can simplify it with having a kind of an amplitude and a kind of a phase shift. So we claim that with this inductors or capacitors or a kind of a combination of inductors and capacitors will lead to an additional phase shift to the original source. Like, so then we can basically evaluate the current and voltages, but with these inductors and capacitors, it basically introduces a kind of a additional phase shift. Either it may be a plus theta or minus theta depending on the energy storing element which we have considered here. Okay, so then what we can simply do is, so we argue that the 6 cos 2t is equals to real part of the 6e to the power j 2t. So then what we can do here is we can assume a scenario where we have our source is a kind of a complex exponential function 6e to the power j 2t. So we found that this is mapped with the real component of this particular function. So then rather having this sinusoidal type of source, we can replace the source with its corresponding complex exponential term. So why we simply say that it's corresponding exponential term? So then see like here the angle is basically appear here and the amplitude appear here. So then with using this Euler's transformation, you can easily map this sinusoidal excitation with its corresponding complex exponential function. So for this particular case, the complex exponential would be 6 times e to the power j 2t. So then what we can then do is, instead of this cosine term, instead of this cosine term, so we assume that there's a source which is basically equal to this. And solve the circuit. So now we have inductor and a resistor and a source. Same circuit, and in addition to the, instead of this sinusoidal excitation, so we have a source of 6 e to the power j 2t. Okay. So then we can continue this evaluation of this current. So similarly, like in the previous case, so we can apply Kirchhoff voltage law. So then we have this LDI or dt. So this is actually the voltage drop across the inductor, which is equals to R times IT. So these two sums of voltage drops basically equals to 6 e to the power j 2t. So if you substitute values, so we basically ended up with this kind of a differential equation. Okay, so this is the differential equation. So then this is the force term. So this is the force term. So then by looking at the force term, we can propose a trial solution for this particular differential equation. So now by looking at the force term, we can propose a kind of a trial solution, which is basically a kind of a exponential function having the same exponent. So this is your exponent having the same exponent. So then we have a different constant e to the power j 2t. So this is the trial solution for this case when you have a kind of an exponential function in your right hand side of the differential equation. Okay. So then the trial solution would be this k e to the power j 2t. So if this is a solution of this differential equation, then definitely this should satisfy the differential equation. So it means once you substitute it here to the original differential equation, it should give the right hand side. So this is the then 4 times k e to the power j 2t, which is equals to 6 e to the power j 2t. So then by equating the coefficients of e to the power j 2t. So this coefficients of e to the power j 2t. We have k e to the power jt. So this we have 2j and e to the power j 2t plus 4k e to the power j 2t equals 6 e to the power j. So then just equating the coefficient, so we can simply take that. K equals 6 divided by 4 plus 2j. Or else if you can simplify, this is 3 divided by 2 plus j. So this is your k value. So in previous scenarios which we discussed during last sessions, so these most of the coefficients are basically real numbers. But for this particular case, if you have an exponential, complex exponential function as a source, so then you basically ended up with a kind of a complex number. Okay, complex number. So how do you then move forward? So now your force response is actually complex number 3 divided by 2 plus j times e to the power j to t. Okay. So then how do you simplify it further? Okay. Now, so in the numerator, so we have complex number 2 plus j. Can we convert it to a polar form? So the polar form would be root 5 e to the power j theta, where theta equals tan inverse half. Okay. So then if you substitute it to this, so then this IFT equals 3 divided by this. So we can replace this 2 plus j using square root 5 e to the power j theta and e to the power j 2t. So if you further simplify, this is 3 divided by root 5 e to the power j 2t minus theta, where theta equals tan inverse half. Okay. So then from this we can claim that if this source is a kind of a 6 e to the power j 2t, we can basically get the force response as 3 divided by root 5 e to the power j 2t minus theta. So then from this previous condition or the previous statement, so the 6 cos 2t is basically equals to the real part of 6 e to the power j 2t. So here we found that 6 cos 2t equals real part of 6 e to the power j. So then by looking at this condition, we can claim that, so the response for this is here. So then we can take the real part of this function, ift, which is equals to this. So here the response is ift. So then if you want to get the response which is map with 6 cos 2t, so take the real part of this response. Okay, so this is the response for this complex exponential, and if we basically derive the 6 cos 2t as the real part of this complex number, you can simply get the real part of the response as a response for this one. So then the response for this is basically the real part of IFT. So actually IFT is the response of 6e to the power j 2t. So then what's the real part of this one? This is equals to 3 over root 5. So this is a kind of an exponential function. By applying Euler transform, you can simply convert it to Cartesian form. So then this becomes e to the power j. So if we apply Euler, so this becomes cos, so this term only, 2t minus theta plus j sine 2t minus theta. So this is the imaginary part. So this is the real part. So then this would be simply 3 over root 5 cos 2t minus theta, and theta is tan inverse half. Okay, so this is the response for the circuit. Okay, so if you summarize this scenario, if you have r cos theta as a source, so we convert the source into r e to the power j theta, where so say sorry where r cos theta is equals to the real part of r e to the power j. Similarly, if you have a r sine theta, so then this becomes the imaginary part of r e to the power j theta. So then, rather having r cos theta, so we basically replace this with r e to the power j theta source. So then find the response, forced response for r e to the power j theta. So then we can replace the sinusoidal excitation with its corresponding complex exponential source and do the calculation for the complex exponential source. So here we found that the trial solution would be k times e to the power j. So if we have a kind of cosine or sine term in the right hand side of the differential equation, so the trial solution would be kind of a cos omega t plus b sine omega t. So then end of the day you have to evaluate two constants a and b. So you have to find both a and b to get the exact forced response. But if you replace this cos theta term with its corresponding exponential, so rather doing this analysis along with the cosine or sinusoidal excitation, so you can proceed the calculation by assuming that there's a source of exponential type which is aligned with the r cos theta source. So then we find this forced response. Here, like, you need to basically find the single constant. So you don't need to worry or to find a two constant like in the previous. So we have only one constant in this system. So you can basically find the k value by substituting this current value to the original differential equation, which should basically need to be satisfied. So then you can easily find the k value. So then you take the real component of this forced response and it is the response, forced response of the source r cos theta. Okay, so the real advantage here is we can easily find the solution because this trial solution would be a kind of a complex exponential one, and we can basically need to find a single unknown constant. But if you are dealing with the sinusoidal excitations, so you basically need to find the unknown constant a and b, which are the coefficients of cosine and sine terms. So then rather finding two unknowns, so it's wise to use this transformation of source to its corresponding exponential function and evaluate the response and take the real part or imaginary part depending on the original source. So then this is the easiest way to get the forced response by converting your sinusoidal excitation to a kind of a complex exponential function. Okay, so this is the stuff what I want to highlight. Yes. Yes. So then next time we'll move to this phase circuits. How do you replace this time domain circuit using a phasor? So we'll discuss it in the next video. So we'll assume that you can basically find the solution forced response for the sources where you for the circuits where you have sinusoidal excitations as well as exponential excitation. So if you have r cos theta, so your trial solution would be A cos theta plus B sin theta. So then you need to find this A and B, two unknown constant. But once you convert this to r to the power j theta and find the trial solution, so this would be k e to the power j theta. So you need to find this constant only, and a single constant, single unknown constant. So then if you take this response, take the real part of this k e to the power j theta. So this is the response, this is the response for cos theta. Okay, so this is the simple summary of this one. So next time we will convert this time domain analysis to phase domain to get the steady state response or the forced response. Okay, thank you.